Hello everyone, welcome back to GDC classes. So dear students, as you all know, GDC English have taken an initiative to launch a new series for YouTube to all the aspirants who are preparing for examinations like GPAT, NIPER, DI and Pharmacist, and that series name is Pharma Thunderstorm. So dear students, this will be going to the first lecture, first session of this Pharma Thunderstorm series, in which we are going to discuss about the subject organic chemistry, and the topic of today's organic chemistry class will be aromaticity. So in today's lecture, we are going to see about the aromatic compounds. What are the aromatic compounds? Why they are have a distinct category and distinct you can say classification in the organic chemistry. So let's get started to the topic of today's class. So aromatic compounds. What do you mean by aromatic compounds and why we have to separately study these kind of compounds? As we all know, like yes, benzene is one of the aromatic compounds that was discovered on the early days. The main you can say concept is revolving around this benzene structure, but yes, there are so many other compounds as well that are non-benzonoid as well, that are actually aromatic. So we'll be going to discuss how we are going to classify any compound that yes, this structure, this compound may be having aromaticity, and of how the aromatic characters enhances the stability. So all these concepts we will be discussing in today's lecture. So first of all, what do we mean by aromatic compounds? So aromatic compounds are basically derived from the word aroma. In Greek, aroma means a pleasant smell, a pleasant odor, means odor that is having a very good, or you can say that yes, it's very pleasing like of odor. So that is aroma. Aromatic compounds are chemical compounds that consist of conjugated planar ring structures. Now this conjugated planar ring structure, that is one of the most you can say criteria, one of the most important criteria for any compound to show its aromatic character. This aromaticity is basically you can say present in the compound that is actually having a cyclic structure. You can say only and only a cyclic structure can have aromatic characters, aromatic properties. So there are some characteristics, there are some properties for a compound that are basic. You can say yes, if the compound is basically following these few characteristics, these few conditions, then only a compound can be said yes, this is an aromatic compound. So we are going to discuss one by one these kind of conditions that a compound must be fulfilling if it is had to express its aromatic character. So the compounds that are also known as aromatics or arenes, all those compounds that are basically having aromatic character are also known as aromatics, or you can simply call them as arenes. Next, we are having all arenes have general formula. Now we will be discussing this general formula in the upcoming slides. So let's get started first of all. So there are only and only four conditions for a compound. Only four conditions. If a compound is fulfilling these four characteristics, these four conditions, then only a compound can be said like yes, this is an aromatic compound. This structure may be a aromatic structure. Why we are discussing this aromatic character? Why we are going to have the cycle ring like yes, this is aromatic? The basic reason behind this compound to show aromaticity is like the stability. In general, we have seen like aromatic compound, if a compound is gaining aromaticity, the compound, that ring, particular that ring will be having a better stability. Like the all classification, all the organic compounds, if we are having, there are various ways to classify. Like one of them is like on the basis of structure, one of them is like you can classify on the basis of presence of functional group. The other classification, that is the aromatic classification. All the organic compound can be basically classified into three distinct classifications, three distinct classes, that are aromatic compounds, non-aromatic compound and anti-aromatic compound. So let's get started. First, if we have to decide like that a compound or that particular structure is aromatic or not, the first condition, if the ring is present, the first condition for a compound to express its aromaticity is the presence of a ring, a cyclic structure. Only and only a closed structure can have aromatic characters. Then later on, the next condition is the presence of planarity. Now this planarity can only be checked by hybridization. As we all know, sp2 hybridized atoms are having a planar structure, and if we have a basic idea of benzene, like yes, benzene is having a flat structure. It's a planar structure. It's a flat structure. The basic reason is all the carbons of that particular ring of a benzene, all the 6 carbons are basically having a sp2 hybridization state, and that's why we can say yes that benzene is a having planar structures. And due to planarity, the next condition arises like that the compound should be a planar structure. Next, the third condition. Third condition is the presence of complete conjugation. The compound must be having a complete conjugation. Now this conjugation is different for other compounds. Like let's get started here. The basic criteria, the basic conditions for a compound to be in conjugation is if it is having like pi bond, sigma bond and pi bond. This is a conjugation structure. If it is having pi bond, sigma bond and lone pair, then you can say yes, the compound must be in conjugation, the system must be in a conjugation. If a compound is having sigma bond, pi bond, sigma bond and negative charge, then the compound is in conjugation. If it is having sigma bond, pi bond, sigma bond and pi bond, sigma bond and positive charge, that conditions is of a conjugation. Next, pi bond, sigma bond and free radical. Okay, free radical. So this is also a case for conjugation. These all are conjugations example. All these are conditions for a compound to exhibit conjugation. Now, let's suppose we are having this. This is a pi bond and this is a pi bond. Now, this system is a conjugated structure, like we are having alternate presence of pi bonds, pi, sigma, pi. So yes, this can be in conjugation. We know very well. Pi sigma lone pair. So yes, there is a pi bond. There is a pi bond and a sigma bond. And let's suppose we are having here nitrogen. And yes, nitrogen is having a lone pair. So let's suppose we are having NH2 and it is having lone pair. Then also this is in conjugation. Like this can be shifted here and this will be shifted to this carbon in the form of negative charge. If it is having pi sigma and negative charge, so we are having pi bond, sigma bond, pi bond, sigma bond, and let's suppose this is having carbon. We are present here with carbon. Let's suppose we are having carbon and CH2. This, the same condition that was happening in the case of lone pair, here also with this negative charge. This negative charge will be shifted to this position and now this pi bond will be shifting to this carbon in the form of negative charge. Pi sigma positive charge. So we know that positive charge is devoid of any electrons. So let's suppose we are having CH2, positive charge. So this condition tells you like yes, there is no any electron in the positive charge. While in negative charge, lone pair, pi bond, we are having electrons. While in this case, this pi bond will be shifting to this position and will be resulting in CH2, positive, double bond, something like this. So this will becoming CH2, positive charge and pi bond will be shifted to this position. Next, what we are having? Pi sigma free radical. Now the free radical, the case of free radical is little bit different, and free radicals are not the case for conjugation in case of aromatic compound, since the next that condition for a compound to express its aromatic character is that is Hückel's rule, that is 4n plus 2 pi electron rule or 4n pi electron rule for anti-aromatic. Now, in the case of free radical is an odd electron. It's a single electron. So, free radicals do not participate in the case of aromatic character, you can say, discussion. So, yes, for the case of aromatic compounds, this condition should not be valid. You will be knowing it later. Why this case is not followed, this condition is not followed for the aromatic compounds. So, these all conditions will be okay for the you can say when we are discussing about the aromatic compound. So let's get started with the aromatic compound conditions. So we have seen 3 conditions. The first condition is the compound must be having cyclic structure. Next, the later on we will be having condition for the flat structure, that is planar structure, and the third case the compound must be fulfilling, that is complete conjugation. Now this complete conjugation, when we talk about the complete conjugation, it means let's look for the example of benzene. Like we are having a benzene structure. Okay, here we are seeing like yes, we are having 6 carbon, and in the 6 carbon we are having 1 pi here, 1 pi here and 1 pi here. So what we are seeing here is like all these pi sigma are present at the alternate positions. So that's why we'll be seeing like, yes, this is having a conjugation. There is a complete conjugation inside the ring. So the next structure will be looking something like this. These both are conjugation structure. You can say simply resonating structures or also canonical structure. The resonating structures are also known as resonating structures or canonical structures. Canonical structures. Okay. So there is complete conjugation of pi electrons inside the ring. So the third condition is the conjugation must be present inside the ring, the complete conjugation of electron. So for the case of pi bond, yes, it is very simple. Like yes, in the case of benzene, there is a conjugation of electron. Let's get to the some examples like we are having, let's suppose, what about this case? A cyclopentane with having negative charge, or a cyclopentane or a cyclopropane. Let's get started with the cyclopropane with having a positive charge. What about these structures? Let's get to the examples of charged structures. So resonance or conjugation, let's see the conjugation in charged structures. Charged structure. Now this charge, what do you mean by charge? Charge means if there is a presence of any positive or negative ion in a ring. As we have discussed earlier, the first condition for a compound to be aromatic is the presence of a cyclic or a ring structure. This aromatic character is only and only present in ring structure, so the compound must be cyclic. And the second one is like the structure must be flat structure. And now, what about these cases? Let's get started. So yes, they are fulfilling the first condition. Like yes, they are having a flat ring structure. Yes, okay. What about the second one? As we all know, hybridization. Carbon is having a hybridization of sp3 and they are having pyramidal symmetry. They are having basically pyramidal symmetry. So this carbon will be sp2 due to pi bond. This will be having sp2 due to pi bond. This carbon is sp2 due to pi bond, while this is also sp2 due to pi bond. But sir, this structure is basically having a sp3, and if the carbon is having negative charge, that is for the case of carbon ion, if it is a carbon ion, it must be having sp3 hybridization, but it won't be having the symmetry of tetrahedral since there is a no bond. One of the carbon is having non-bonded, but they are actually having negative charge. So they are basically having a charge structure. So the geometry will be pyramidal. Same like we are seeing for the case of nitrogen, sp3 hybridized nitrogen. Okay. So what do you now think? Sir, this won't be having the aromatic character. Why? Since it is not fulfilling its second condition. What was second condition? The compound must be a planar structure, a flat structure. But in this case, this carbon is having pyramidal structure. So, okay, these four carbons are having flat structure, but this won't be a flat structure. Okay, so what this compound must be? It is won't having aromatic character. We will be discussing it later on. Okay, what about this one? Okay, sir. Sir, anion. Sir, carbon with having anionic charges having sp3 hybridization. For example, if we are having CH3 negative, so this is the structure of having CH3 H and we are having a negative charge. So this is a pyramidal structure, and if we are having carbon with positive charge, let's suppose we are having CH3 positive, so this will be having a structure of something this. It's a planar structure. It's a planar structure with a vacant p orbital, unhybridized p orbital. So this is a planar structure. This will be having a planar structure, while this will be having a pyramidal structure. This will be having a pyramid-like structure. It's a non-planar, while this is a planar. Planar, okay. What kind of planar? Trigonal planar. So yes, this is a sp2 hybridized carbon. This is also sp2 and this is also sp2. Okay. Okay. So yes, all the carbons are having sp2 hybridization. So yes, this compound, this cyclopropenyl cation will be having a planar structure, flat structure. All right. So now let's get started to the fourth condition and the last condition for a compound to show aromaticity. Last condition to show aromaticity, that is Hückel's rule. That is Hückel's rule. Now the Hückel's rule tells you if the compound is having 4n plus 2 pi electrons in conjugation, the total number of electrons that are basically present in the conjugation, that will be equivalent to 4n plus 2. And by solving this, 4n plus 2 is equals to total pi electrons. If we are finding the value of n as 0, 1, 2, 3, 4, 5, 6 and so on, a whole number, that means yes, that particular structure will be having a aromatic character. And let's suppose we are having total number of conjugated electrons, the complete electrons in conjugation that are actually taking part in conjugation is equal to 4n. While n, we don't know what will be the n, we have to find out this value of n. So 4n is equals to total electrons in conjugation. Now if we find out the value of n as 1, 2, 3, 4, 5, 6 and so on, a whole number, that will be having an anti-aromatic character. Okay, so now the fourth condition will be the last condition for a compound to either it could be aromatic compound or anti-aromatic compound. But like let me write down first. 4n plus 2 pi electrons in conjugation. In conjugation, that tells you about the aromatic compound. This will be telling you about the aromatic. Aromatic, for a compound to show aromaticity, for a compound to become aromatic, we must be following this. And for a compound to express anti-aromatic, the total conjugation electron will be 4n is equals to total pi electrons in conjugation. Now this pi electron do not means like yes, they are only having pi bonds. It could be either positive charge, that is 0 electron, a negative charge, that is 2 electron, a lone pair, that is also n2 electrons. 4n is equals to pi electrons in conjugation. If we are fulfilling this case, then the compound must be having anti-aromatic characters. Anti-aromatic characters. That will be anti-aromatic compound. Okay. So this was just for this was all about aromatic compound and anti-aromatic compound. Just 4 rules. Now, all right, sir, finished, done? No. Now let's look for the examples. How a sp3 hybridized carbon can also be a flat structure, and there are many variations, there are many exceptional cases as well. Now one by one we have to look for all these concepts and understand a compound, how it become an aromatic compound. So as we have seen just right now, a compound that is having negative charge means carbon ion, how that can be, okay, let's suppose we are having this. So let me copy this structure, 1, 2, 3, 4. Let's suppose we are having a pi bond here, and a negative charge. So yes, we know like this is having a negative charge. It is a cyclic structure, correct. It is having conjugation, yes, there is complete conjugation, but there is a doubt, like a compound, an atom, a carbon having negative charge, that must be having a sp3 hybridization. So let's get started. Yes, it could be a sp3 hybridized if the electrons, if the negative charge is only and only present, that is a, you can say it is a localized on a carbon. But since this negative charge is in resonance, it is in conjugation. So what happens here is, like this will be shifting to this position. This pi electrons will be shifting here to make a new pi bond between this and this carbons. If this carbon is making a pi bond due to this negative charge, then it must be breaking this bond and this electron will be shifted to this carbon. So what happens here is, like we'll be saying something like this, and this negative charge has moved to the next carbon. Next carbon, okay. So this was sp3 when the negative charge was present at this carbon. But what about now? Sir, it is having sp2 hybridization, okay. Okay. Means negative charge is actually moving. It is in a delocalization. Okay, what about next? Now this negative charge will be moving to this position and making a new pi bond between these and these carbons. While this carbon will be breaking this bond and shifting in the form of negative charge to this carbon. Okay, so new negative charge here and these kind of structures. Now the sp3 carbon, the carbon that is having negative charge here, now is having again in sp2 form. Okay, the next case, this will be shifted to this position and this will be shifting again to this position. Now negative here and here and here. Okay, again what happens is, let me draw some other clones of it. What happens again here is, we will be seeing like this negative charge will be moving to this position and this will be moving to this position. Correct? So what happens here is, we are having pi here and this negative charge in the pi bond at this and negative charge at this position, at this carbon. And now next what happens? This will be shifting to this position, while this again the same, the first one. This and this. Oh, sorry. Okay. So now look all the structures very carefully. All the carbons of the cyclopentadienyl anion structure, basically, this negative charge is present on each of the 5 carbons. First, here, 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 and here. All the 5 carbons. So if we simply draw the hybrid structure, we can say like this is having a complete conjugation, complete double bond, and this negative charge is present throughout. And this negative charge is present throughout the ring. Means all the carbons are basically having partial negative charge character. This negative charge is not localized to a specific carbon. It means all the carbons, like if we are talking about, let's deeply look the case for this. We have negative charge on this carbon, while other canonical structures, the other forms, in the one form only we are having negative charge on this carbon, while on the 5 other cases, like 4 other cases, we can see there is no negative charge on this. Means there is only 1/5 time this negative charge is present on this carbon. That negative charge is actually in delocalization. So that means yes, all the carbons will be counted as sp2 hybridized, since the delocalizing electrons, the conjugating electrons will not be considered in the case of conjugation for the case of negative charge. Since that charge is actually moving, that is actually in motion, So we can see, like we can draw like all the carbons will be having partial negative charge, but partial, it means all the ring carbons will be having a sp2 hybridization only, means a flat structure. So yes, it's a cyclic one. First case, it's a ring that is cyclic. The next condition, that is the compound must be having planarity. So yes, all the carbon will be considered as sp2 and it's a flat, or you can say planar structure. So yes, that is planarity, that is planar. And the third, that is the compound must be having conjugation. Yes, the complete conjugation of electrons is present. There is a complete conjugation inside the ring. So yes, that is conjugation, complete conjugation. And the next case, that is how many electrons are actually taking part in the conjugation. So you have to be very careful For this last case, the last condition, how many electrons are basically taking part in the conjugation? So let's see. We can see there is a two pi bonds, two of the pi bonds are in conjugation and a negative charge, and one negative charge, and one negative charge is in conjugation, correct? Now, whenever there is a pi bond, the pi bond must be made up of two electrons. This pi bond will be also having two electrons and a negative charge. The negative charge will be having two electrons. Now we have to write down here. Negative charge is having two electrons. A positive charge is having zero electrons. A lone pair is having two electrons, and a pi bond is having two electrons, while a radical is having one electron. That's why we have not included a radical, since we have to find a complete number, complete whole number. If we have a radical, a single, a odd electron conjugation, it means we never ever find out a complete whole number by solving 4n plus 2. So we are having one negative charge in conjugation and two pi bonds. So from two pi bonds we will be having four electrons, one pi bond consisting two electron, four for two pi bonds, and a negative charge means two electron. So four electrons from here, two electrons from this complete makes six electrons. So total electrons, complete electrons in conjugation are 6 electrons. Now we have seen if the complete electrons in conjugation, the total number of electrons in conjugation is equal to 6, we have here. Now let's put this 6 electron in 4n plus 2 for aromatic and 4n for anti-aromatic, and now find out the value of n. So 4n plus 2 is equals to 6. Now let's short it. We'll be having 4n, and let's shift 2 to this. So 2 is in plus here, so it will become in minus. So we'll be having 6 minus 2 for this. 6 minus 2, 4. So we'll be 4n is equals to 4. So n is equals to 4 by 4. Okay, 4 by 4, that is having 1. That is having 1. Okay. So yes, by solving 4n plus 2, total pi electrons in conjugation, we are actually ending with a complete number, with a whole number, that is 1. That is 1, not fractional, not in decimal. So yes, this will be aromatic structure. Now let's find out for the anti-aromatic. Is it an anti-aromatic compound? So 4n is equals to 6, n is equals to 6 by 4. We will be ending up with 2, oh my bad, 4, 1 time 4. So 2 by 3, correct? 2 2s are 4, 2 3s are 6. You can also say 1.5. It's a decimal or fractional. So no, this condition is not fulfilled. Yes, but this condition is fulfilled. This was the case for the compound to express aromatic, and this was the case for compound to express anti-aromatic. So that structure, that is cyclopentadienyl anion, is not an anti-aromatic compound. It's following this rule. So yes, that compound is having aromatic structures. It's an aromatic compound. Let's look for some other examples as well. You have seen the case for benzene. Okay, we are having benzene. What do you think? This benzene is actually having cyclic structure. Cyclic structure. It is having flat structure, planar structure, or all the carbons are having sp2 hybridization. It's a conjugation. Complete conjugation of electrons is present in this ring, in this structure. 3 pi bonds. Now we are having 3 pi bonds conjugation. 3 pi bond. 3 pi bonds mean 3 pi bond means 1 pi bond constituting 2 electrons. So 3 will be constituting 6 electrons. Again we are having 6 electrons. Now if it is following 4n plus 2 is equals to total electrons in conjugation, that is 6. Now find out 4n is equals to 6 minus 2. 6 minus 2. 4n is equals to 4. N is equals to 1. Yes, the benzene is having aromatic character since this will be following all the rules. It's a aromatic ring structure. Okay. Next case, we are having, let's suppose we are having cyclopentadienyl cation. Cyclopentadienyl cation. What do you think for this one? Positive charge? Correct. This will be shifting to this position since there is no any electron. So both the electrons will be moved to this position, this pi electrons, and making a bond, making this carbon a positive center, electron deficient center. Okay, again this will be moving to this position. So a new pi bond will be forming here, and this carbon will be having deficiency of electrons, that is positive charge. Again, this will be moving to this, and positive charge will be shifted to this carbon. Again, this will be moving to this position, making a pi bond to this and a positive charge to this one. Okay. Now again we are saying this will be shifting to this position, making a pi bond here and positive charge to this side. The same. All these are canonical structures, that are resonating structures. Now we can see, yes, we are here having complete conjugation of electrons. And what are total number of electrons in conjugation? Now we are having a cyclic structure, we are having a planar structure. How planar? All the rings carbon are having sp2 hybridization. Yes, it's a flat structure, it will be a planar structure. So here it's a planar structure. Complete conjugation of electron is present in the form of 2 pi bonds and a positive charge. So 2 pi bonds will be giving you 4 electrons and 1 positive charge. One positive charge do not have any electrons, so it will be having 0 electrons. So total electrons in conjugation will be 4 electrons. Now if we are having 4n plus 2 is equals to 4 electron, and the value of n 0, 1, 2, 3, 4 and so on, it will be an aromatic structure. And if it is following 4n is equals to 4 electron, yes, it's saying okay, 4n is equals to 4 electron, n is equals to 1. So yes, it will be following anti-aromatic rule. What about this 2, 4 minus 2, that will be having 2, that will be 1 by 2. So this will not be fulfilled here. This case will not be fulfilled here. You can see 4 is equals to 4 minus 2. So 4 minus 2, 2. 4n is equals to 2 by, n is equals to 2 by 4, that will be 1 by 2. So this will be not having aromatic character, but this structure is basically having an anti-aromatic nature. It will be having anti-aromatic characters. Okay, so this is the case for the cyclopentadienyl cation. Now some other examples, and one more note point. If any of the condition is not fulfilled by the compound must be having a non-aromatic structure. That structure will be a non-aromatic structure. Like if it is not cyclic, non-aromatic. If it is not having planarity, non-aromatic. If it is not having conjugation, complete conjugation, it will be a non-aromatic structure. And if it is having, it is not following the 4n plus 2 or 4n rule, it will be also become a non-aromatic compound. So we are basically having 3 compounds: aromatic, non-aromatic and anti-aromatic. Like let's have a case, like we can see this structure. We are having pi sigma pi, but no condition for the conjugation around this carbon. So this ring, the complete ring, is not in conjugation. It means it's a non-aromatic structure. Due to, you can say here, like due to absence of conjugation around this carbon, due to absence of conjugation around this carbon, this structure will be a non-aromatic structure. Non-aromatic structure. Non-aromatic structure. So, the condition for a compound, the most important is stability. The aromatic compound are the most stable compounds, and this is a question in many of the competitive examinations. The order of stability. An aromatic compound is always more stable than non-aromatic compound. Non-aromatic compound, while a non-aromatic compound is always and always more stable than an anti-aromatic compound. Anti-aromatic compound means anti-aromatic compounds are least stable. Are least stable. And this is the case for stability of aromatic, non-aromatic and anti-aromatic compound. You have to write it down, and this is important one. This is important one. Okay. So now if again look for some other cases, look for some other examples as well. Like we are having cyclo, or I simply write it down, cyclo penta dienyl cation and cyclo penta dienyl anion. Which will be more stable? Which will be more stable? Which will be more stable? What do you think, guys? We are having cyclopentadienyl cation here, cation and anion. Dear, tell me. We know, like, yes, this structure is having total 4 electrons in conjugation, 2 here, 2 here, no electrons in the positive charge, while this is having 2, 2 and 2, 6 electrons in conjugation. And we have seen the cases. A cyclopentadienyl is an aromatic structure. It's an aromatic structure. Aromatic, while this is having anti-aromatic structure. This structure is anti-aromatic. So what do you think? This will be less stabilized than this one. Due to aromatic, this cyclopentadienyl anion will be more stable. More stable. That the stability rule. So this will be more stable than the cyclopentadienyl cation. Now, there is a short trick as well. How to find out a compound is aromatic or not. You don't have just look for the complete 4n+2 conjugation rules. Don't worry about it. You simply remember always CpCO and CpCe. Just remember these two formulas. That is, if the compound is having cyclic, planar, conjugation, and odd electron pair in conjugation. It will be aromatic structure. It will be an aromatic structure. Okay, it will be an aromatic structure. While if the compound is having cyclic, planar, conjugation, complete conjugation. Let me write down as complete conjugation. Same here. Okay, or just write down conjugation, and we have CpCe here, and even electron pair in conjugation. So if the complete electron pair in conjugation is equals to even pair of electron in conjugation, then this will be the case. This will be the case for aromatic, while this is for Anti-aromatic. The compound will be aromatic. The compound will be aromatic if it is following this rule, and if the compound is having this rule, the compound will be anti-aromatic. So CpCO and CpCe, just two tricks. You can say tricks. These are the tricks. And now let's have some examples as well. Let's go for some examples. Let's move for some examples. Suppose we are having this structure and we are having positive charge here, negative charge here. Cyclopropenyl anion, cyclopropenyl cation. Now this cyclopropenyl anion, since you can see, is having one pair of electron here in conjugation and a negative charge is present. So the complete electron pairs in conjugation will be two pairs. One pair here in the pi bond while the other pair is in the form of negative charge. So complete electron pairs in conjugation will be equal to 2. So yes, this is a cyclic structure. It's a planar structure. Again, this pi bond will be, this negative charge will be in conjugation. So you won't consider this negative charge as carbon as sp3. Just we have discussed the case for the in the cyclopentadienyl anion. Cp, yes, it is having complete conjugation. This will be like, suppose, let's write down some structures. This will be moving here. So this will be having negative here. Again, the carbon, this moves here, produces negative here. So negative here and this one. Okay. Okay. And this moves here, gives this one. So same. Okay, so yes, there is a complete conjugation. Now how many electron pairs are in conjugation? So one pair here, one pair here. So one here and here, two pairs. Got it? Let me write down as one pair here, one pair in pi bond. So there are two pair of electrons in conjugation. A negative charge, two electrons, that means a pair. A pi bond, that is two electrons, that means a pair. So we are having two pairs, that is CpCe. This is the case for anti-aromatic. That will be the case for anti-aromatic. Got it? What about this one? What about this one? There is a positive charge. Electron moves here, shifts pi bond here, gives positive charge. My bad, moves there. So positive charge here. Got it? Next, this will be moving to this position. My bad. This will be moving to this position. Moving gives you positive charge here and pi bond here. Again. This moves here and positive charge will be shifted to this position, resulting in positive here and a pi bond here. So yes, there is a complete conjugation of electron. Yes, it's a cyclic structure. Cyclic. So see, it's a planar structure. The structure is planar. The complete conjugation is present here. Complete conjugation of electrons is present. Complete conjugation. And what about electron pairs? There is only and only one pair. Why one pair? Positive charge do not have any electrons. Positive charge are electron deficient carbons. They do not have any electrons in conjugation. They are actually electron deficient center. And the high electron density centers like negative charge, lone pairs or pi bonds moves to that particular positive charge. So yes, they do not have any electrons. The only and only electrons in conjugation are present from the pi bond. So yes, they are having only and only one pair of electron. And if there is only one pair of electron in conjugation, you can simply write down as odd electron pair. Odd electron pair in conjugation. Odd electron pair in conjugation. So what we have got? It's a CpCO. CpCO. It means yes, this structure will be an aromatic structure. Let's have the Hückel's rule as well. We are having total electrons in conjugation 4. 2. So we are having 4n plus 2 is equals to how many electrons pair are in conjugation? 2 electrons. 4n is equals to 2 minus 2, that will be 0. 2 will be shifted to this. Let me write down as 2 minus 2, that is a 0. 0. So 4n is equals to 0. N is equals to 0 by 4. If 0 is divided by a number, it always gives you 0 as result. So that's why I have told you, for the case of aromatic, if we are having 4n plus 2 is equals to electron pair in conjugation, and the value of n starts from 0, 1, 2, 3, 4 and so on, a complete number for aromatic. And if we are having anti-aromatic case, the n value starts from 1, 1, 2, 3, 4 and so on, a complete whole number. Yes, there is a case for 0 for the case of cyclopropenyl cation. Okay, so this is the case for aromatic. Now we are having another structure, that is cycloheptatrinyl cation. We are having cycloheptatrinyl cation. Now just tell me what this structure will be. This will be your homework. That you have to write me down in the comment section, the answer. You can simply write this structure as tropylium. Okay, tropylium, and IUPAC name as cycloheptatriene ill cation. So simply apply the formula CpCO or CpCe, aromatic, anti-aromatic. Okay, now let's get to the cases in the PPT. So these were the rules. Now Hückel's rule, you can see GPAT, NIPER, GUJRATI and many of the pharmacist examinations as well. Hückel's rule is used to determine the possession of aromatic properties. This was the question. Hückel's rule is used for to describe the aromaticity, to discuss about the aromatic properties. Hückel's rule stated mathematically that all planar aromatic compounds must have 4n plus 2 pi electron, where n is a positive integer or 0, starts from 0, it means aromatic. And if it is having anti-aromatic compound, it must be having n value from 1 to 3. Aromatic compounds are comparatively stable due to presence of resonance energy and delocalization of electron clouds. Okay, next we are having structures and examples. Benzene, cyclobutadiene. Okay, so cyclobutadiene, one of the most easiest example for a compound to express anti-aromatic characters. This is anti-aromatic. Why? We are having cyclic. Okay, we are having planar, all the carbons are having sp2 hybridized. Next, conjugation. Yes, there is complete conjugation of pi electron, pi sigma, alternate positions of pi sigma arrangement. How many electron pairs are actually participating in the conjugations? One pair from this pi bond, the other pair from this pi bond. So we are having two pairs, and 2 is a even number. So this structure is following CpCe. Simple. It's a anti-aromatic structure. And the next, the last one, that is non-aromatic. Now we have some of the examples, that you can say some exceptional examples for a compound, that by applying this CpCO, we can simply predict yes, it's aromatic or anti-aromatic. But some of their exceptional cases, as always, you can say there's chemistry. So without exceptions, chemistry is not possible. So let's get some exceptional cases, exceptional examples. One of them, like, okay, so this is for the 4n plus 2 and 4n, simple. We have discussed this. And we are having some examples. Like, but first let me discuss that cyclooctatetraene. Cyclooctatetraene, here and here. This is simply known as cyclooctatetraene. Cyclooctatetraene. What do you think about this? Just looking at the appearance, just looking at the structure, we can simply predict like yes, this structure will be having a cyclic, a planar, conjugation, and total number of electron pair, one pair, second pair, third pair, and fourth pair. So 4 pi bonds means 8 electrons means 4 pair of electrons. So yes, this will be having CpCe like appearance. But what about this P? Always remember, if a ring, if it's a monocyclic ring, it's a single ring with more than 7 carbons, up to 7 carbons, okay. But if it is having more than 7 carbons, the ring will be having non-planar geometry. If it may be having non-planarity. The same case happens here for the case of cyclooctatetraene, and it's an exceptional case. Actually, due to a monocyclic ring structure and 4 pi bonds in just 8 carbons, so there is a strong strain. You can say this structure actually will be facing stronger strains and leads to non-planar geometry of this structure. This will be looking like this, but actual structure for this is something like this. It's a tub-shaped structure. It's a tub-shaped structure. Tub-shaped structure, and you can say yes, it's a non-planar structure. And we have discussed if any of the compound, any of the condition for these will not be fulfilled, then the structure moves to the non-aromatic. So yes, this is actually looking like it's an anti-aromatic structure. It is actually looking like CpC. So yes, it can be an anti-aromatic compound, but due to this non-planarity, and let's be very clear, this planarity is only and only due to hybridization. We are checking this planarity on the basis of hybridization, and hybridization does not 100% assure you like yes, this ring or any of the carbon will be having non-planar geometry or planar. We were just taking help from the hybridization, but actual appearance, actual geometry of the structure cannot be predicted just by hybridization, just not by hybridizations. So yes, this planarity is, you can say, sometimes exceptional for few of the cases. And that's why we can say less due to non-planar geometry, due to tub-shaped geometry, this cyclooctatetraene is not anti-aromatic. It is looking like yes, this is an anti-aromatic structure. It is not anti-aromatic, rather it's a non-aromatic structure. It's a non-aromatic structure. It is rather a non-aromatic structure. Okay, non-aromatic structure. So this was the case for cyclooctatetraene, one of the exceptional case due to tub shape, due to non-planar symmetry. Cyclopropenyl cation, one pair, okay, it's a aromatic one. Anion, non-aromatic, my bad, anti-aromatic. Cation, anti-aromatic. Anion, cyclopenta one, cyclopenta, it will be aromatic structure. Now, there are some cases for the heterocyclic as well. Like this is furane. Now you can simply write down how a furane structure is, or a you can say thiophene or pyrrole is basically a aromatic. Why? It's a pyrrole, you can say. Yes, we will be having one pi bond, and a lone pair. So this moves here, this moves here, this moves here. There is a complete conjugation of electrons, and all one pair here, electron, one pair here, one. So we are having two pi bonds. Two pi bonds and one lone pair. And one lone pair. This all gives you 2, 4 electron, 1 into 2, that is 2 electron. So 2 pair here, 1 pair here. So we are having 3 pairs. You can say 6 electron. 6 means it's a aromatic one. So we are having 3 pairs. That is a odd pair. So it will be following CpCO. It's a aromatic one. Same with the furane. Now for the case of furane and thiophene, we know we are having 2 electron pair in the form of lone pair in thiophene and furane. But always remember, there will be only and only one of the lone pair will be in conjugation with the ring, the other won't be in conjugation. The conjugation exists only with a single species in an atom. If it is having more than one condition for conjugation inside an atom, only one of it will be used. So let's suppose this is B, this will be the case for aromatic conjugation. So yes, one pair, two pair, three pair, we are having three pairs in conjugation. It is also following CPCO, aromatic one. Same with the thiophene as well. Same happens with the thiophene as well. And what about pyridine? Now we are having pyridine. We are having pyridine. We know we are having pyridine and we are having a pi bond and a lone pair on nitrogen. Now we are having again, nitrogen is having lone pair as well as pi bonds, but the conjugation will be existed only by pi bonds. There will be no involvement of this lone pair inside the resonance. We can see, yes, the resonance can only happen due to this pi bonds. So what is the need for lone pair to participate in the conjugation? No. It actually destabilizes the structure. If it is having only pi bond conjugation, it is okay. We are having complete conjugation due to these pi bonds. So yes, complete conjugation, and this structure will be aromatic region. It's same benzene like appearance, same benzene like structures. 2 pi bond, two electron, 2 here, 6 electron, that is 4n plus 2 is equals to 6, n is equals to 1. So we will be having furane as a aromatic one, furane as aromatic. Next, thiophene and pyrrole, benzene. Now we can see here we do not have conjugation around these carbons. For the pyridine as well, it will be an aromatic structure. Cycloheptatrienyl Now I know I have given you homework about this question, but 2 electron here, 2 here, and no electrons. So we are having actually CPCO. Only 3 pairs of electrons are actually in conjugation in tropylium. So yes, that will be a aromatic one. Naphthalene, anthracene, all are known as polycyclic aromatic. They are more than one cyclic ring. Yes, they are polycyclic aromatic compounds. It can be naphthalene, it can be anthracene, it can be phenanthrene. All are polycyclic aromatic compounds. All are polycyclic aromatic compounds. Okay. All right. So let's discuss some of the questions. First question here is, among the following organic compound, the one that is non-aromatic, which will be a non-aromatic one? We have clearly discussed like radicals cannot ever participate in the conjugation for the cases of aromatic compound. Reason, if they are odd electron, radicals are having single electron, and single electrons, if the single electrons is participating in the conjugation, it can never leads to a complete number when we are solving 4n plus 2, or 4n can never be have a complete number. So yes, this is benzene aromatic one, cyclopentadienyl anion aromatic, cycloheptatrienyl cation aromatic, but this is a non-aromatic. This can never leads to aromaticity. Can never. So D will be the right answer here. D will be the correct answer. Which of the following is anti-aromatic? What do you think? Which will be anti-aromatic? Oh my god. We have answer here. But let's get discussing here. We are having benzene aromatic, cycloheptatrienyl cation, an aromatic one. Cyclopentadienyl anion, we have discussed. This is also an aromatic. While this cyclopentadienyl cation, CPCE, only 2 pair of electron in conjugation due to just 2 pi bonds. Since positive charge don't have any electrons in conjugation. So CPCE, that is anti-aromatic. D. Which of the following is not aromatic? Which will be not aromatic? Pyridine is an aromatic structure. We can simply know. Benzene, yes, it's an aromatic one. Cyclohexene and thiophene. So yes, thiophene is an aromatic one. Thiophene is aromatic. What about this cyclohexene? Cyclohexene simply is saturated 6 carbon ring structure. This is cyclohexene. Cyclohexene. Oh, okay, let me write down. Cyclohexene. It's a cyclohexene, so you have 1 pi bond only. Cyclohexene. It means just a single pi bond. Benzene is actually cyclohextriene. Cyclohextriene. So this is cyclohexene. No conjugation. So can't be a aromatic one. So it will be a non-aromatic due to no complete electron pair conjugation. C will be non-aromatic. Which of the following is not a heteroaromatic compound? Which will be not an heteroaromatic compound? Cyclohexane, pyridine, pyrimidine or pyrrole. Cyclohexane, you can simply ask, you are asked about heteroaromatic. Heteroaromatic means the ring that is actually having one of the atom other than the carbon. What about pyrrole? We are having pyrrole as this one. What about pyrimidine? Pyrimidine, okay, 1, 3 nitrogen. So this is pyrimidine, it's a aromatic ring. Pyridine is also a aromatic ring. Pyridine is also a aromatic ring. But this cyclohexane is having just this. So how it can be an aromatic? No, not at all possible. But yes, these all three are heteroaromatic, but this is a non-aromatic actually structure. So A is the right answer for this. Which of the following is not aromatic? Which is not aromatic? Thiophene is an aromatic. Pyrrole, furane. So we know pyrrole is a aromatic structure. Pyrrole, furane is a aromatic structure. Thiophene is a aromatic structure. Thiophene is a aromatic structure. Dioxane. Dioxane is this. It can either be 1/6 oxygen in a saturated 6-member ring, or it can be 1,2 dioxane, or it can be 1,3 dioxane. All of them are dioxane, and they are just saturated versions. They do not have any electron pairs in conjugation, complete conjugations. So this will be a non-aromatic, non-heteroaromatic compound, dioxane. Which is correct about aromatic compound? These are following Hückel's rule. Yes, they are actually following the Hückel's rule. They are cyclic compounds. Yes, they are cyclic compounds. These having localized pi electrons. Just one thing, these are having localized pi electrons. No, they do not have localized. Basically, they are having delocalized pi electron. So this option is incorrect. Now, these are following Hückel's rule. This is 100% time correct. All time this will be correct. These are cyclic compounds. Now let me be very careful. Cyclic compounds, they can be a right answer, but now we have to prefer for the most appropriate, since we have this as a wrong answer. So these are cyclic compounds. Yes, they are cyclic compound, but this is not 100% true. Like all the cyclic compounds are aromatic. We have seen, like, no, this is not necessary. Like all the cyclic compounds are aromatic compound. So either you write this as the 100% appropriate option, or if this is correct, then this must be having a delocalized electron pairs. So if this is mistake in this question, if there is a mistake by NIPER, like they have forgot to write down as a delocalized, then okay, this will be the right answer. But by looking and just if I just by my presence of mind suggest the answer, this will be the 100% time true. Hückel's rule is actually the condition for a compound to express its aromatic character. But this is not 100% true, like all the cyclic compounds are aromatic. No, there are some cyclic compounds that are non-aromatic. There are some cyclic compounds that are actually anti-aromatic. So this is not 100% correct. This is, since already wrong, this won't be the correct. Only A can be the right answer here. Very true. So this is the tricky question asked by NIPER. You have to be very careful while solving these kind of questions. Select the correct statement for phenylethrene, polycyclic aromatic carbon. Okay, polycyclic phenylethrene is 3-member, 3-cyclic ring structure. Okay. Oh, my bad. Polycyclic. This 3-benzene in non-planar fused structure. That is non-linear structure. Heterocyclic, not at all possible. Polycyclic, non-aromatic, no, it's an aromatic one, 3-benzene ring. This is not a heterocyclic. Only A is the right answer. That is polycyclic aromatic. Which of the following is anti-aromatic compound? So this is non-aromatic. Cycloocta, non-planar tub shape geometry. Anti-aromatic, anti-aromatic, and that will be a anti-aromatic, CpCe, anti-aromatic. Pyrrole is a aromatic structure. What has been asked? Anti-aromatic. Which of the following is anti-aromatic? So this is also anti-aromatic and this is also an anti-aromatic. That is aromatic, this is non-aromatic. Anti-aromatic have been asked. Okay, so both of them can be correct. B and C. B and C. Okay, B and C both are correct. Let me correct you. This is also correct. That is also having CpCe. If this structure is cyclopenta dinyl anion, then it will be an aromatic, while cation will be an anti-aromatic structure. Both are correct. Order of stability. So aromatic, most stable, wrong, wrong. Then non-aromatic, wrong. A will be the right answer. Least anti-aromatic. Which of the following compound is aromatic? What do you think? Anti-aromatic? Pyridine is aromatic, non-aromatic, non-aromatic due to absence of conjugation. So B is the right answer. Which algorithm is used for anti-aromatic system according to Hückel's rule? According to Hückel's rule, that is total number of electron pair in conjugation must be having 4n plus 2. So 4n plus 2 is equals to n, that is total number of electron pair in conjugation. As L is this n is actually about total number of electron pair in conjugation. So yes, that is actually correct. This is not correct. This is not correct. This 4n is equal, this is for anti-aromatic. So this is for anti and this is for aromatic. So what we have to discuss? Anti-aromatic. So this D will be the right answer. D will be the right answer. Hückel's rule is related to acidity, basicity, reactivity. No, this is about aromaticity. The compound is aromatic or not. So we basically decide by Hückel's rule. Which one of the following is the correct statement about aromatic hydrocarbons? Correct statement about aromatic hydrocarbon. They have only sigma bonds. No, they are actually having sigma as well as pi bond. They have only pi bonds. Only pi bonds? No, that is not correct. They have one sigma, two pi bond. They have sigma and delocalized pi bond. Very true. They are actually having sigma and pi bond, but the pi bonds must be having delocalization of electron. That pi bond must be in conjugation. That's why we have seen delocalized pi bond. So yes, D will be the right answer. D will be the correct answer. D is the correct answer. So dear, this was all about the first class, the first session for your Pharma Thunderstorm series. I hope you guys all enjoyed this session, and I hope you all like and tell me how was the session. Let me know in the comment section. Thank you so much. We'll be meeting very soon with one of another lectures, one of the another topic in the organic chemistry. Thank you so much, everyone.